micro delay is over, yeah? Yes. The micro delay is over, yeah? Okay. Okay. Yeah, good evening, everybody. First of all, I would like to say thank you to Vladas for organizing such a great summer school and for providing such a good atmosphere and possibilities here to give talks. And last but not least, to invite me here. Thank you very much. Yeah, and all your helpers, of course, you are not alone. Yeah, okay, I wanted to give you a survey on the parabolic Anderson model. I don't give you the latest and not the strongest results, but I try to explain to you what the spirit of this model is. So the parabolic Anderson model is basically the Cauchy problem for the heat equation with random potential, and we have localized initial datum. So we look at the partial differential equation on ZD, where U, this is the solution, this is a function of time, t is positive, and Z, this is in ZD. So U satisfies this equation here. The time derivative is equal to the discrete Laplacian applied to U plus multiplication with a random field xi. And I start with the initial condition that at 0 we have 1 and anywhere else we have 0. So xi, this is an IID random potential. It has values in the real numbers, including minus infinity, but not plus infinity. And yeah, I'll tell you later what kind of distributions we are looking at. For a long while, I will not tell you anything about this. This triangle with a D reminds you for discrete. This is a discrete Laplace operator. Later, maybe also the continuous one appear, and then I need a different symbol. So therefore, I put a D there for discrete. The operator on the right-hand side, this is the so-called Anderson Hamiltonian. This plays also an important role in mathematical physics. It's sometimes called a random Schrödinger operator. Some few words about this come a bit later. Some technical remarks are in order. So the solution U of t comma dot, this is a random, time-dependent, and in distribution shift-invariant field. This is the main object of our study. We want to know, we want to see what we can say about the large T asymptotics of the solution. But let's mention that the existence is guaranteed under a mild moment condition on the potential, which I'm assuming here. So we do have a solution, and we have just one solution here. And another thing is interesting because we also want to take moments of the solution U, and for this we need to assume something about moments of the potential, and we just assume for a while that every positive exponential moment of the potential is finite, and then the solution U of t comma dot can, has even moments of all orders. So I could, for example, look at the expectation of U to the P for any positive P. Where does this model come from? So first of all, it's a model for random mass transport through a random field of sinks and sources. What is a sink and what are sources? You can, I'm going back to this formula here, you can see it as a model for particle at time 0. You have one particle at the origin and nowhere any other particle. And then the particle starts running and carries a certain mass, which is initially 1. Yeah? And if the particle is in a point z with psi of z being positive, then the mass is increased exponentially according to the time that it spends in the point z, and then it calls up the point z a source, because the mass is exponentially increased according to the time that the particle spends there. And if z is a site such that psi of z is negative, then the mass of the particle is decreased, and I call it a sink. Or you could also say it's a trap. For example, if psi of z is equal to minus infinity, then the particle is immediately killed and you don't have any mass anymore. This is an absolute trap. You can also give an explanation of the solution or an interpretation of the solution as the expected particle number in a branching random walk model in a field of random branching and killing rates. So you have now a branching and migration model where you start with one particle at the origin at time 0. This runs like simple random walk, and it runs through a field of branching and of killing rates. And these are the random variables which are expressed in terms of the xi. So these are basically the branching and killing rates. And a particle can be killed with a certain exponential probability, and it can be split into two with the probability given by the branching rates. And if you then form the expectation over the migration and over the random walks and over the splitting and killing mechanism, then u of t comma z is nothing but the expected number of particles in z at time t. So this is another interpretation of the solution. So it can be seen also as coming from some branching walk model, branching process walk model. And another interesting remark is the Anderson-Hamiltonian, the operator on the right-hand side. This is an operator which is heavily studied since decades by people in mathematical physics because it describes conductance properties of alloys of metals or optical properties of certain glasses with random impurities. And the main open question is, what does the whole spectrum look like, and how can the eigenfunctions be characterized? Do they exponentially localize or not? This is the big question there. These questions refer to the whole spectrum from the beginning to the end. But we are not concerned in our talk with the whole spectrum. We are looking at time to infinity limits, and therefore we're staying all the time at the boundary of the spectrum. We make assertions at most about the principal eigenfunction, eigenvector, but not about the whole spectrum. But they're close connections, yeah? So you could also ask questions about the spectrum close to the boundary, and this has much to do with the large T asymptotics of our model. So this is a connection to random Schrödinger operators. Yeah, you saw some background literature and surveys. Maybe you feel better if you see a formula for the solution. It is possible, in terms of the famous Feynman-Katz formula, to write down what the solution is. So u of t comma z is exactly equal to this expectation here. So x of s is a simple random walk in continuous time on zd. The generator is just the Laplace operator, the discrete Laplace operator. And it starts from z under pz. So here it starts from 0. And it ends at time t at z. And what do we have in the expectation? We have e to the integral from 0 to t of xi of xs ds. So in other words, we sum up in the exponent all the values of the potential xi that the random walk sees up to time t, weighted with the time that it spends in the respective points. So if it spends long time in a point z, then xi of z is multiplied with a large number in the exponent. So basically, this is something like expectation of e to the t times something. And we are looking now at the large T asymptotics, so it must have to do something with extremely large values of something, and the something is what you have basically in the exponent. So our question about large T asymptotics has much to do with the way of thinking like in extreme value theory, but more about this later. So the main goal is say something about the large T behavior of the solution. In particular, and this is basically what I'm doing today, we discuss what is the large T behavior of the total mass of the solution. What is the total mass? It's just the sum over z of everything. This is nothing constant. This is, if you go back to the Feynman-Katz formula, this is just dropping this last factor here, and the only thing that we're studying is the expectation of this exponential stuff here. Once more precisely, the expectation goes only over the random walk, and it is a random variable in terms of the xi. Yeah? So it's a complicated function of the values xi of z. Important is the notion of intermittency. This is something which has been discussed in the 80s already in a very general manner. The parabolic Anderson problem is supposed to be one of the simple models in which you can make some mathematical efforts to give a strict meaning to what intermittency really is and to understand it much better. What is intermittency? It's very simple in plain words. For large T, the main contribution to this total sum here comes indeed from only small and few islands which are far away from each other. So the total sum over all the z is not necessary in order to catch the total mass. It's enough to take only a relatively small sum over those z in which the solution is extremely large. So you should think of the U as being a field which has extremely high islands and a large C of almost zero values between them. And these islands are t-dependent, are randomly located, of course, and they are so pronounced, so extremely pronounced, that the total sum is asymptotically the same as the sum only over the islands. So this is an intuitive definition of intermittency. Of course, it's difficult to make this definition here mathematically precise, and then it's even more difficult to give a proof of this. Okay, here are some comments about these islands. So these islands are randomly located, depend on t somehow. So the size of the islands depends on t. The height of the potential in these islands depends on t. And they're not too far from the origin because I started with the mass at 0 at time 0. And the mass needs some time to spread out. So the typical distance is maybe something like t, but not square root of t. It has nothing to do with central limit theorem or something like that. Yeah. These islands are basically defined by the fact that the solution and also the potential psi are extremely large in these islands. So basically it comes from those islands in which the potential psi is extremely large and where the islands are sufficiently broad. Then the potential can make use of it. Intuitively speaking, the mass flows to this part where the psi is extremely large and stays there all the time up to time t in order to get as much as possible from positive values, from extremely large values of psi. And if this island is a bit too small, for example, then it costs you a lot that the mass stays in such a small area, so therefore it should be a large island in order really to contribute. So you have to find somehow a compromise of extremely high islands which are sufficiently broad. And they, in a certain sense, maximizing over the largeness and the broadness of the islands, they will give the main contribution. And then, of course, the solution is then also extremely large. And now I'm going a bit deeper into the... I want to quantify what is now precisely the good measurement in terms of which you can say what is a good contribution coming from an island. It is indeed the largest eigenvalue of the Anderson-Hamiltonian. In mathematical physics language, it's the bottom of the spectrum of minus Laplace, minus psi, in these large, in the large t-dependent box. And more precisely, these large eigenvalue in large t-dependent box comes from the small islands because the local eigenvalue is also extremely large there. The eigenvalue in the large box comes from a maximum of the eigenvalues in the small boxes inside, there where the potential is extremely high. Pictures are to follow. So this means we have to do something like extreme value theory for the potential psi. In a certain way, we have to find maxima of the potential of an RD field and have to see how the maxima are standing together. How many of these points where psi is large are standing together such that we have a broad island. So it's clear that the whole asymptotics should depend only on the upper tails of psi of 0, not on more details. So you should know how the asymptotics of the probability that psi of 0 is large is, and only on these asymptotics the answer should depend. There's another definition of intermittency which is much easier to formulate and much easier to prove in cases. Okay, I'm assuming that the pth moments for any p positive of the total mass is finite, and then you can write down this object here. So upstairs you have the p norm of the random variable u of t, downstairs you have the q norm, and intermittency can be defined by requiring for p smaller q that this limit is equal to 0. So this quotient here is always smaller or equal to 1, of course, because of Jensen's inequality, but the requirement is that this one goes to 0. And in seminal work on this model by Gärtner Malchanov 20 years ago, They first of all show that in this sense intermittency holds practically everywhere as soon as the potential is not constant. And secondly, they give also an intuitive explanation why this simple limit here is really in accordance with the intuitive definition I gave a minute ago. So they identify certain islands which carry the pth moments, which carry the qth moments, but not the pth moments. So those parts of the space which generate the growth of the pth moments are different from those ones which generate the qth moments. And only in this way it can happen that the quotient really goes to 0. And typically it goes very heavily to 0, very quickly. Now I'm coming to an announcement of 4 universality classes. This is something which you might ask in the beginning, what kind of potentials should I look at? I have myriads of potentials. I can take this distribution, that distribution, and so on and so on. Isn't it a sea of distributions in which I don't know which one I have to take? It turned out after a couple of years of collecting examples that there are indeed only 4 different universality classes. And I will mention the most important of them today, but not all of them. The double exponential distribution, this comes explicitly a bit later. This is one of the prime examples because it's also technically more easily to handle than the others. A certain boundary case, then bounded potentials and almost bounded potentials. I explain you later what this all means. These are 4 different classes. They depend only on the definition of the upper tails of the potential xi in a certain way. The asymptotics of the large values of xi, they give you the classification of the 4 classes. I will later along the talk explain to you what the difference is. But first, let me tell you what has been shown yet and what are the most important papers, as I think. So, very natural questions are how large are the islands, how large is the potential and the solution there, and what do the shapes of the potential and the solution look like in the islands. And let me mention that there, in 2 main special cases, there was already a very strong kind of answer. There, so the one case was a double exponential distribution, which I'm going to explain to you a bit later. And the other case was done by Snitman in a series of papers. This was the continuous analog for Brownian motion among Poisson obstacles. Yeah? In this case, he has similar questions, and he gave also a very strong answer. So he identified certain islands such that the complement of the islands give a negligible contribution to the main mass. So this is, in my opinion, the strongest sense in which you can answer this question. And in both cases, it's also shown that the potential and also the solution approaches a certain deterministic shape. This is a minimizer, let me call it phi, of a certain deterministic characteristic formula. I will give you examples a bit later. And, okay, the potential approaches the minimizer of the formula, and the solution approaches the corresponding eigenfunction of Laplace plus phi. So this is basically the rough answer. So the potential xi, maybe after some rescaling, looks like a given function which is determined by some minimization problem, and the corresponding solution, the solution u of t comma dot, looks like the corresponding eigenfunction in these islands, locally. I give a more precise statement about this a bit later. There are also weaker answers to the same questions in a couple of cases. This means basically that the moment asymptotics of the total mass and the almost sure asymptotics of the total mass have been identified in terms of certain variation problems. And there you see that certain islands give the main contribution, but it has not been proven that the complement of them is really negligible. It's basically shown, look, there is an island, and this gives already asymptotically the same contribution as everything together. So this island is already dominant. But they don't show that the complement of them is negligible. How many islands have to be taken into account? There, I must say, rough bounds, t to the small o of 1 cannot be improved according to their proof method. So t to the small o of 1, this could be still quite large, but this is the best that you get out by the methods in these 2 papers. The conjecture is that it's only finitely many, maybe only one island. But this is, as far as I know, open for the cases we are looking at. I tried to find a proof for this together with Marek Biskup, but this will take some while. And it has been proved for kind of potentials which does not have exponential moments, heavy tail potentials. If I have time, I can explain to you what we can prove in this case here. Here we can prove that just one island is enough. But this is also a special case. Now I want to give you heuristics for the asymptotics of the moment of the parabolic of the total mass of the solution. More precisely, I give you two heuristics. The first one is on this slide here. Here I use Fourier expansion, and on the second slide I do something like a dual way. So what I'm doing here is basically, if I take the moment of u of t, and u of t is itself an expectation. U of t is an expectation over the path, over a random path. And now I take the expectation over xi of this. We have two expectations inside each other. Here I first carry out the expectation over the path and see what I can do for this. And on the next slide I first carry out the expectation over the xi and see what I can do for the path. So let's first look at this one here. This is basically well known, I guess, because I'm doing just the standard Fourier expansion for the operator Laplace plus xi with zero boundary condition in a large cube. Okay, instead of t, you can take also 2t or t squared or something else. That's not so important. Yeah. So we have now the eigenvalues, the kth eigenvalue of the potential, Laplace plus xi, and the corresponding eigenfunction. They form an orthonormal system, and the one corresponding to the principal eigenvalue is positive. Then we have the expectation of u is the expectation of its Fourier expansion. Here you have the sum over all Fourier, over all eigenvalues. No? Phi k of 0 because we're starting 0, and phi k against the constant function 1 because the terminal condition is just 1. And now I introduce a function h of t which has not yet appeared. This is an important function. I will tell you later what it is. For a while, let's say that h of t is some function, a deterministic function, much larger than t. So I pull out e to the h of t, and here I give it back to the potential xi, and of course I shrink the total sum together to the sum and for k equal to 1, because this one is the largest. The exponential factor for k equal to 1 gives the largest exponential contribution, so I can neglect all the others. Okay, and here I do some cosmetics. No, not really cosmetics. What I'm doing here is to look with the eyes of an expert of large deviation theory at this object here. Because this is something to which you might be able to apply in large deviation principle if the object xi minus h of t divided by t satisfies a large deviation principle. So if xi satisfies a large deviation principle, what does this mean? This means basically this here. If the probability that this object, the shifted field xi, looks like a given function f, phi is just some function, not an eigenfunction. No? If this probability can be written as e to the minus t times some large deviation rate function L of phi, then I say that this object here satisfies a large deviation principle. So here I have an exponential way to write down the decay of the probability that this shifted potential looks like a given phi. And here I have e to the t times some function of this one. L lambda 1 is a function of this one. And if I put these two things together and hope the best because of missing continuity and boundedness and so on, yeah, and apply Varadhan's lemma, one of the cornerstones of large deviation theory, then I get that the exponential rate of this one here is given by e to the t times a certain supremum. And here you have the supremum over all possible functions phi, or all possible shapes phi, of lambda 1 of phi, as you see here, minus what you have to pay for the event that the potential looks like phi. So this is a crash course in large deviation theory, so to speak. Yeah. It is one example in which you can apply in LDP. If you have good asymptotics, exponential asymptotics for probabilities like that, and if lambda 1 is a well-behaved functional of these objects, then you can heuristically write down that this large deviation statement should be true. Of course, there's a lot of work behind it because lambda 1 is typically not continuous and typically not bounded. Yeah, once more the same in words. We have a large deviation principle. On the event that psi looks like this here, we have an exponential contribution to the Fermat-Katz formula, which is precisely h of t. This is the term outside here, no? Plus t times the eigenvalue of Laplace plus phi. And the probabilistic price is e to the minus t times L of phi. And now you have to make the relation between the two and optimize over all shapes of phi. So maybe I give you a small picture what the moment asymptotics look like. So what is the picture that you should have in mind for the moments? So the potential psi looks as follows. So in a certain ball around 0 with a certain radius, and the radius is something which I did not introduce yet, alpha t. In our case, alpha t is just of order 1. This is just a scale function which I have to introduce in general, and in this example it's equal to 1. And outside this ball, the potential does just something, and inside this ball, it suddenly does something extremely crazy, which gives the best contribution to the moments. So this is a rough picture for the potential psi. So in a box with a certain radius alpha t, the psi tries to have extremely high values. What does it mean? It has something of values of order h of t divided by t, which is large. In our case, h of t divided by t goes to infinity. And this is an island of size of order alpha t. And here the difference between maximum and minimum in this area is of order alpha t squared. I didn't tell you what alpha t is, but now I can tell you what are the 4 different universality classes in terms of the behavior of alpha t and h of t. Yeah? So the classes are the following. The first class is where alpha t goes to 0. Even this is possible, which means that the picture shrinks together to just 1 point. Then the island is just a singleton. And here, h of t divided by t is extremely large. The second one is where alpha t can be taken equal to 1. This is the case that which you see in this equation there. So the assumptions that I did here for the L of phi, they are the ones which you have in the class number 2. And here, h of t divided by t is something like log t. Yeah, because of this. Yeah, this calculation is the one for class number 2, where the alpha t is not there, so to speak. Yeah. So this is the one where alpha t is of finite order. So the box here has a finite order, say 15 or something like that. Yeah. And you have only finitely many points in which this potential has to assume very high values. This is class number 2. This is what you see on the screen. The third one is where alpha of t goes to infinity, but is extremely slow. So alpha of t goes very slowly to infinity, something like logarithmic or something like that. And here, the h of t divided by t is roughly is something like log t to the small o of 1. So also this one goes still to infinity, but very, very slowly only. And the fourth class is where alpha of t is like a certain power of t, nu is a positive number, and h of t divided by t goes to 0. So this is the case of a bounded potential, where the potential has its essential supremum equal to 0. So this is in a nutshell, these are the 4 classes, the asymptotics. And here, what you see there is a heuristic calculation for class number 2. Now I'll show you the dual the calculation for the same object. So what I'm doing here is I solve the same problem with a completely different approach. I keep the random walk fixed for a while and take the expectation over the xi. And I have to introduce the so-called local times of the walk. There's an important object here. This is the amount of time that the random walk spends in z between time 0 and t. And now I finally show you what h of t is. It's nothing but the logarithm of the moment generating function of the potential. H of t is this one here in all the cases, also here. And h of t over t is, of course, a function which tends to the essential supremum of the random variable. And this explains why the absolute height should be something like h of t over t, because h of t over t is something like the maximum of the random variable. Okay. So we write now the moment of u of t in terms of this one here. This is something which you can easily calculate because formally we had here in the Fermat-Katz formula just the integral from 0 to t, psi of the random walk, and now I just do it, I organize this sum in slightly different. I take the sum over all z, psi of z, and multiply with the time that the random walk spends in the point z. Here I just interchange the two expectations, and now I want to carry out this expectation here. By the way, I didn't mention that these brackets mean expectation with respect to xi. So here, this is just Fubini. I change the order of the expectations. And if I carry out the expectation here for fixed LT of z, then you have basically products of independent random variables, so you can do some elementary steps and end up here. So this is equal to this one here by just using independence and the definition of h. So what you have really is now an expectation of an exponential functional of the local times. Now you do some cosmetics. You again pull out the factor e to the h of t, and you organize the rest such that it is t times some function of lt over t. Lt over t is normalized. No? Lt over t has L1 norm equal to 1. So this is an interesting object. And then you have to define, of course, phi t of this in this form here. And if you use this notion here, then you see that this is just a piece of cake. Yeah. And we are in this class here, and then it's relatively easy to show that this one here, this object here, has a wonderful limit. If t goes to infinity, then you end up with this formula here for this function here. So this function is basically this functional here. Rho is some parameter in the game, which I didn't mention so far. Yeah. So what you have here is basically a non-t dependent function of lt over t, precisely this function here. And now you use once more a large deviation principle for this one here, but now for the lt over t, which is well known since 30, 40 years. Here, Donska-Varadan in the mid-70s and also Gerdner in the mid-70s, they showed that the probability that the normalized local times look like a given function psi runs like e to the minus t times the function of psi, and the function is wonderfully explicit. This is the rate function for normalized local times. Yeah, and if you use once more Varadan's lemma and large deviation arguments, then you see that this one here should behave like e to the t times this supremum here, supremum over all local time shapes, so to speak. Phi, this is this one here, phi of the local time, minus the rate function of the local time, so to speak. And this variation problem is our second answer to the question, what is the asymptotics of the moments of u of t? Certainly this function here, this variation problem, must be the same as this one here. But this is no problem to see. If you insert the Rayleigh-Ritz formula for the largest eigenvalue, yeah, which is itself a suprema or something, and interchange the suprema, then you see that the two formulas are the same. So these are two ways to identify the moment of u of t. and they both lead somehow to proofs. So this, okay, maybe the proofs are not so direct as you see it here, but they are really the basis of certain proofs for the parabolic Anderson problem. Okay, let's go to more concrete formulas now. I show you now the explicit formulas for the double exponential distribution. What is the double exponential distribution? You have a parameter rho, and the upper tails are given by this. Yeah, the name is maybe a bit childish. You see where the name comes from, no? Exp and e to the. This is the only reason why we call it the double exponential distribution. I think people from statistics would say this is one of the extreme value distribution. Maybe they have another name for this, Weibel, or I don't know. It's Gumbel, yeah? It's not precisely Gumbel, no? After some shift or some elementary transformation is necessary. Okay. For this distribution, you see that the h of t is basically rho times t times log rho t, as I promised here already. Yeah. And now you can make much more explicit formulas. Basically, this is the same as I showed you right now, but here I reveal what really the rate function for the potential is. You can explicitly calculate that this function here is the rate function for the potential. So this is basically the same formula as I explained to you a couple of minutes ago in the first of the two heuristic calculations, with explicit identification of what the large deviation rate function is. This is the formula here. And here's now a bit blah blah. Basically the same as I gave you in the last 10 minutes. So therefore I don't go once more through it. Basically this blah blah here explains this picture. Yeah, maybe you ask me, what does the picture mean? Once more, the interpretation of this picture is the contribution from fields xi, which look like what you see in the picture here. This is optimal on an exponential scale. So if you take the expectation only over those xi, which look like that here, look like that means the xi should look like the minimizer of this formula here, yeah, then the contribution coming from this one is already what you wanted to have for the whole contribution. So the main contribution is concentrated on behaviors of the field xi like that here. If you have chosen the optimal potential phi here from the deterministic characteristic variation problem. Now, moment asymptotics. This is different because, almost sure asymptotics. This is different from moment asymptotics because of the following. For moment asymptotics, you have two different kinds of independent randomnesses, the path and the potential, and they work together. Each of them does something crazy, what it never would have done usually, but it's the optimal way to do both crazy things such that the best compromise comes out of it. So both work together. In the almost sure case, it's completely different. The psi is as it is, and the random walk has to deal with this. So typically, the pictures are now much different. A bit too wet here. Almost surely it's the following. So typically you have to look in a much larger box, something like t, maybe t times log squared of t or something like this. And the potential xi looks like maybe this here. So this is a possible picture for the potential psi. And the random walker now stands at the origin, looks at the landscape of the potential, and decides now what it wants to do in order to gain as much as possible from the potential psi. And therefore it looks around, where would it be great to stay as long as possible? Which is the best island which I should visit for a long time in order to get as much as possible from the high values of the potential? Maybe this one is immediately seen as the best value because it's extremely high. It could be even much higher. Yeah? But the thing is, it is a very narrow island. If the random walk would try to get something from there, then it would immediately rush there, of course, and then it would stay all the time here, precisely in this small island. But this is not so good because it costs you a lot to be in such a small, narrow area. Much better is this one here. It's not as high, okay, but here you have a much broader island. So here the relation between cost and gain is much better. So if I would be the random walk, I would think about this island or this island. I would rush there, spend there almost all the time, and then I have an extremely large contribution. Then, of course, you would like to know how high is this, and what is the shape of Xi close to the top. And these are things which I can describe in terms of variation problems, but they look now a bit different. And this is what we have now in this variation, in the theorem there. So almost surely it's slightly different. First of all, you have to rescale, you have to replace t by log t in this way here. This is something that I cannot explain at the moment so well. And the characteristic variation problem looks now a bit different. You take the supremum over all top eigenvalues of shapes phi, such that the large deviation rate function small a equal to d. This is to be explained in the following way. This condition here tells you that the potential phi is not too crazy. It has a certain least amount of probability. So the probability that phi appears somewhere is not too small. This is the criterion that you can show that such a potential really appears somewhere. So the minimizer, the maximizing potential phi, really appears, for example, here. So this is an area in which the phi appears as around the top of the potential psi. Why? Because it is not too crazy. And among all them which appear somewhere sometime, you take the one with the largest eigenvalue. This is an optimization procedure. So if I have identified these two things of approximately the same height, then I take that one whose shape close to the top is giving a better lambda. And if I take the optimum there, then I see that this gives you the large deviation statement for the almost sure almost sure asymptotics. This blah blah is what I told you in the last 5 minutes. Let me mention, but not so much in detail now, let me mention that we have for this particular distribution also identified islands such that the complement is negligible. What would be the islands in this picture here? So I would take this center point of the first island, and maybe I would take this one here. So gamma of t is just the set of these 2 points. Yeah, and so in this picture, you have gamma of t consisting of 2 points only. So the statement is, you have a random set gamma of t with not too many points, such that the distance between any 2 points of them is very large. Okay, here the distance is almost t. And you see here, if you take the subsum only over the R box about all these points, then asymptotically it's already everything. So this means that the complement doesn't produce any interesting amount. And here you see also that the shifted potential in this picture here looks like any maximizer of the variation problem that I gave you just a minute ago. And the corresponding solution looks like a certain deterministic constant times the corresponding principal eigenfunction, as I announced half an hour ago. This is one of the universality classes also. This is what I explained to you. The second one is the one where you take rho in a certain way equal to infinity. There's a certain rho in these formulas here. And if you take rho equal to infinity, then you have the class which I called here number 1. The third one comes on the next slide. And the fourth one is a kind of continuous version of the first one. What I call here the third one is number 4 here, and what I call here the fourth one is number 3 there. I will not give you the formulas for the fourth one. The third one is on the next slide, but I think it is better not to present it to you because of time reasons. I have some other plans with you. Aha. I wanted to tell you something about the relation to random Schrödinger operators, something that I announced 3/4 of an hour ago. What can you do with asymptotics for the parabolic Anderson problem, for the integrated density of states of the random Schrödinger operator? So this goes as follows. Let me look at the spectral measure of minus Laplace minus xi in a large box QR. So this is this one here. So you take the normalized measure on the negative eigenvalues. So this number is the eigenvalues, k from 1 to number of points in QR. And this is the spectral measure in the box QR with some boundary condition. What you call the integrated density of states is this limit here. You take this measure of the interval from 0 to e. By the way, I'm now looking at bounded potentials. Now I'm imposing the condition that the essential supremum of xi of 0 is 0. So this is a potential which is always negative, but comes as close as possible to the value 0. And therefore, I take here 0 as the boundary of the spectrum. 0 is then the boundary of the spectrum. And I'm looking now very close to the boundary of the spectrum. I count how many eigenvalues per volume you have in the narrow, small interval close to 0 at the boundary of the spectrum. This is what we call the integrated density of states. And the question is now, what is its behavior as e goes to 0? And we can give an answer which is very rough because you have lots of logarithms here. But this is a surprising answer because earlier it was discussed that for bounded potentials you should have always the value minus d half. And we show now that for any parameter smaller or equal to minus d half, you can find a potential for which you have this number as this limit here. So the appearance of any other number than minus d half was somehow a certain surprise for the community of mathematical physics, of random Schrödinger operators. This goes as follows, roughly. You look at the Laplace transform of this measure here. Later I make r to infinity. Laplace transform of this measure in the parameter t. So here's the formula. And I write it in terms of this measure here, then it's this discrete sum. And now I use this as a kind of Fourier expansion for something which is almost the parabolic Anderson problem. So the sum of these eigenvalues without any factor here, this is equal to this Feynman-Katz formula. Here you have a certain boundary condition at the boundary of QR, and you end up at the same point at which you start, and then you sum over all points. So this is the Feynman-Katz formula for this sum of eigenvalues. And this is almost the same as what we study for the moments in the parabolic Anderson problem. As r goes to infinity, it goes precisely to this one here, according to a ergodic theorem. So basically what here is nothing but the Laplace transform of the integrated density of states. And now we can look at the large T asymptotics, and this is what you can draw from my result with Marek Biskup for this case, which I didn't give you. It behaves like this here, and this alpha of t is what you see here in the picture. Yeah? So we can find the large T asymptotics like that, and then you have to invert the Laplace transform, which is a piece of cake, and then you end up here. And then you have shown that the asymptotics t goes to infinity of the parabolic Anderson problem are in one-to-one relation via this Laplace transform to the small e asymptotics of the integrated density of states. This is the connection. And in the last 5 minutes, I would like to show you another class of potentials which admits an extremely strong localization assertion. I have mentioned it already. I take a distribution now which has extremely heavy tails. So being large is for this potential an extremely simple task. This is the Pareto distribution, the heaviest tail that you can use here because of some restrictions. So the probability that psi of 0 is larger than r runs like only like a polynomial with parameter larger than d. This does not explicitly belong to the classes I have shown to you here because h of t is equal to plus infinity. I have not positive exponential moments. I cannot put it into this class structure here because h of t is immediately equal to plus infinity. But you can, if you like to, see it as a certain subcase of this one here, of the first case, where h of t is so large that this is satisfied, trivially, so to speak. So we do have a solution, but the total mass has no moments. We cannot look at moments. What we do now is to look at probabilities, or let's say at weak assertions. The first main result here is due to Remke van Hofstad, Peter Mertens, and Nadia Silrava. We have a weak asymptotics for the rescaled total mass. So you take 1 over t logarithm of u of t and multiply it with this precise factor of t over log t, and then its distribution converges to something which you can explicitly identify. So we have an explicit formula for the right-hand side. So this means the term 1 over t log u of t has the same weak asymptotics as the maximum of t to the d independent Pareto variables with parameter alpha minus d. So in a certain way you can interpret this as the assertion that the random fluctuations of the potential, or let's say the extremely high values of the potential, they completely dominate the smoothing effect of the Laplace operator. Or you have the corresponding picture to this one here is you have one extremely high value in your box with radius t, and everything else is much, 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 much smaller. So the difference between highest island and second highest island is extremely large. And in other words, you can do the following. So it's well known. If you have a sum of RID heavy-tailed random variables and require that the sum is very, very large, then what they're doing, they're not doing this in the sense they're doing it in the following way. Just one of them is extremely large, basically the value you require, and all the others are of moderate size, just like the expected value or something like this. So this is the typical way how heavy-tail random variables make their sum large. Just one has to do the work, and all the others are smaller. This is well known. And this is now the same picture for the parabolic Anderson problem with this Pareto distribution, with the heavy-tail distribution. And this can be formulated in a wonderful way as a highly concentrated assertion. There's just one t-dependent and random, of course, point, zt, which dominates the whole sum. So if you take u in the sum just over the single summand and divide it by the total sum of everything, then in probability you get the limit 1. So this is an extremely strong concentration property. Everything comes from just one island, and this island is a singleton. And we can also say something about the asymptotics of the point where this is attained. This is joint work with Hubert Lacroix, Peter Mertens, and Nadia Silrava. So the conclusion is there's just one of these intermittent islands, and this is a singleton. This is an assertion in probability. You have to change it slightly bit if you want to have an almost sure statement, because the process z of t jumps. This is a small obstacle. So the assertion in almost sure sense is slightly different, but almost the same. Okay, let me close now with a list of open problems and further questions. So one question for me is still, is just one island enough? And what is the contribution from the other island, from the second best island, third best island, and so on and so on? I hope to say something about this together with Marek Biskup. Hope also to say something more precise about the relation to Anderson localization, at least close to the boundary of the spectrum. something about the exponential localization of eigenfunctions for the top eigenvalues. Another interesting subject is, I have talked all the time about localized initial condition. Certainly you can also look at homogeneous initial condition. And what is the transition between these two different initial values? In a certain way, you can interpolate between them. In a certain way, if you mix over large boxes, then this is a kind of interpolation between that kind of solution and that kind of solution. There are already some works by Benarus, Molchanov, and Ramirez, but still some open problems. The next thing is, you could make you put a front factor in terms of your diffusion operator and let it depend on time. Which means if sigma of t, the front factor in front of the diffusion operator, is faster than 1, is larger than 1, then you accelerate your diffusion. And if it's smaller than 1, then you decelerate the diffusion. And new phenomena arise, and we could identify two different critical scale functions, an upper critical scale, and a lower critical scale. This is all contained in the recent thesis by Sylvia Schmidt. And another interesting subject is where you replace the front factor in front of the Laplace operator by something that depends on, why do I write time? On space, of course. I want to let it depend on space and a new randomness. So the sigma of x are RID random variables. This is a kind of randomly perturbed Laplace operator, and it's also known under other names. What is the typical name for this? If you put weights, also you could put also the weights not on the sides, but on the bonds between. Random conductance model. I was looking for this word. Yeah, this is random conductance model. I'm doing this together with some PhD students without external potential at the moment, just looking at the eigenvalue asymptotics in large boxes for this operator alone. This is an interesting subject. In the future, we want to switch on also the external potential. And another interesting direction is aging properties of the model. So you want to see what the problem does at time t at some much larger time in comparison, t plus s of t. And one of the easiest ways is to look at the time correlation between these two times here, large time t and an even much larger time t plus s of t. So this is the correlation between them. And you want to understand what the limit t to infinity is and want to interpret this in terms of aging properties of the whole system. And there's some interesting work going on at the moment with Jürgen Gärtner and Adrian Schnitzler, which should be finished in the next months. Okay, so I hope I gave you a bit of the spirit of this model, and I hope that you have understood at least something. Thank you. In which class? So at the moment, yeah, it seems to be very difficult for any of these classes. It's, you know or no? It's done actually in a class where you have just 1 point islands. So very heavy-tailed class, yeah, as a beginner, as a starter. Certainly the goal must be that we understand that also in any of these classes here, yeah. But at the moment, this paper is for 1 point potentials. I mean potentials which lead to a 1 point island in the large T limit. In probability, yes, I believe. Almost surely could be not true, yes. But in probability, and this is how we work at the moment, we try to prove it in probability, similarly to the very heavy-tailed potentials. Yeah. We try to do some eigenvalue order statistics, such that we can really, in distribution, identify the difference between first and second eigenvalue in particular. At least the eigenvalues are different. the largest eigenvalue and the second largest eigenvalue do have a gap. And this gap can be quantified somehow in terms of limiting distributions. And this should be enough in order to show that the whole contribution from the island, maybe in connection with its distance to 0. Yeah, maybe this also comes into the game. Yeah.